Okay, so in this video, we're going to focus in on solutions. Remember, solutions are the only mixture that is homogeneous. That means it looks the same throughout the entire container of the solution. And solution is just that special name for homogeneous mixture, all right? But we still need ways to describe the solutions that we have. And so on the screen right here, you'll see a picture of 4 test tubes that each have a solution in them. Notice it's homogeneous throughout each test tube. But what this picture is showing you is solutions that are what we call more concentrated or solutions that are more dilute. Okay, maybe you've heard these terms before. When I was a kid, we used to make orange juice from concentrate, right? So in the freezer section, there were these cans of really concentrated orange juice, and we'd put it in a pitcher and add water to it, and we'd have our orange juice. What we were doing by adding water to it was we were diluting it. So what this is referring to is, remember I told you that every solution has 2 parts to it. One part is the solute, the other part is the solvent. Let me move this solute word so you can see it a little bit better. There we go, solute and solvent. The solute is the part that is being dissolved. The solvent is the thing doing the dissolving. So if you think of like sugar water, right? Sugar is being dissolved in the water. Therefore, the sugar is the solute. The water is the solvent. If you've ever had Kool-Aid as a kid, right? Little packets of powder that you opened up and poured into a pitcher of water. The Kool-Aid, excuse me, the Kool-Aid was the solute, the water. Sorry, the water was the solvent. So the more water you added, the more dilute it would have been. Okay. So we have a number of different ways that we can describe how concentrated or how dilute a solution is. And this chart that I have here is in your textbook, and you can look at it there. We're going to be looking at the first 4 of these ways to describe concentration of a solution. Basically, how much solute is in your solution, right? I want you to notice that we will not be dealing with mole fraction. So you can just cross that one out. Don't need to pay attention to it. It is in your book. I won't be giving you any homework on it. Won't be on your test. But you will need to know percent by mass, percent by volume, molarity, and molality. So when we're looking at this, as you can see, these are all ratios. They are comparisons in some way between the amount of solute and the amount of solution, or the amount of solvent, depending, right? On the first 2, they're percents. Remember, I told you that a percent is always the part divided by the whole times 100. Well, if you look at the formula here, mass of solute, that's the part that we're looking at, how much solute is in this solution. And then the whole is the mass of the solution, the total whole, times 100. If you look at percent by volume, it is almost identical formula. You're just looking at the volume of the solute and the volume of the solution rather than the mass. When we get to molarity and molality, these are slightly different. So molarity, you're going to look at moles of solute divided by the liters of solution. That's your formula for molarity. Molarity is always abbreviated or, shown as a capital M. So you might see something that says, 3 molar hydrochloric acid solution, right? That means that you've measured that solution based on its molarity. Then we will look at molality. Again, as you would think from the name, it does look at the moles of the solute. But now, instead of the liters of solution, you're going to deal with the kilograms of the solvent. Okay, so that's something you want to pay attention to, is that slight difference when we go to calculate molality. Molality is always abbreviated as a lowercase m. So you might have a 2 molal solution of something, and you would write it like that. Okay, just some standards to know. Let's look at how we do these calculations. So here's a sample problem. In order to maintain a sodium chloride concentration similar to ocean water, an aquarium must contain 3.6 grams of sodium chloride per 100 grams of water. What is the percent by mass of the sodium chloride solution? So percent by mass, remember, we're going to want the part divided by the whole times 100. Remember, the part in these is the solute. So this is going to be mass of solute divided by the mass of the solution. Remember, we want the whole, not another part in there. This is key on this one. So what is your solute? Is it the salt or is it the water? Well, one thing to keep in mind, always, 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 water is a universal solvent, right? So if water is the solvent, can it be the solute? And the answer is no, it can't be. Water is the solvent in these problems. So therefore, sodium chloride is your solute. So we have 3.6 grams of sodium chloride. Now we're going to divide this by the total mass of the solution. When you figure this out, you've got to incorporate both the mass of the solute and the mass of the solvent. So this is going to be 100 grams of water plus 3.6 grams of the sodium chloride for a total of 103.6 grams. I'm going to go ahead and fix that a little bit. You then would multiply it by 100 to get your total. Okay, so when you calculate this, you'll have 3.6 divided by 103.6 times 100, and you will find that you will have a percent by mass of 3.47%. Remember, with percents, we always go to the hundredths place. Okay, so let's look at this one. If a 100.5 milliliter IV solution contains 5.1 grams of glucose, what is the molarity of the solution? The molar mass of glucose is 180.16. So molarity, that's your capital M. Remember, that equals moles of solute divided by liters of solution. Sorry guys, it's late and it's been a long day for me today. Liters of solution. So we have to look at this. One of the nice things in these problems is they often will identify the liters of solution. If you notice, 100.5 milliliters of IV solution. So that's going to be your denominator. However, we need liters. Remember, to convert milliliters to liters, we move our decimal point to the left 3 times. 1, 2, 3. So that means we have 0.1005 liters of solution. Now we have to find out how many moles of solute. Glucose is sugar that's being dissolved in the water. That's our solute. But they gave us grams. You've got to remember how to turn grams to moles. So if I have 5.1 grams of glucose, use my conversion factor, 1 mole, and they did the math for us. They tell us that the molar mass is 180.16 grams. So 5.1 divided by 180.16, that gives us 0.0283 moles of glucose. That's going to be our numerator. And when you calculate this, you're going to get 0.282 molar solution. That's the molarity. Okay, now we'll come back up here and use molarity. So very often what happens in chemistry labs and many biological labs as well is instead of keeping millions of solutions of all different concentrations, what the labs will do is they'll keep a large bottle of a very concentrated solution. And then each scientist will come and take whatever they need of that to dilute down to the concentration they need. The way they do this is by using a formula that is molarity 1, volume 1 equals molarity 2, volume 2, right? So whatever is the molarity and the volume of the stock solution that I need, that's going to equal the molarity and the volume of my diluted solution that I want. So let's look at a problem. If you know the concentration and volume of the solution you want to prepare, you can calculate the volume of the stock solution you will need. So what volume in milliliters of a 2 molar calcium chloride solution would you use to make 0.5 liters of a 0.3 molar calcium chloride? Notice the 0.3 molar is a smaller molarity. That means it's more dilute. It's less concentrated. So we know that our stock solution is 2 molar. We want to know what volume we need to take of that in order to have a 0.3 molar solution and to have 0.5 liters of it. So we divide by 2 and we discover that the volume we're going to need of our stock solution is 0.075 liters. Well, now they ask for this in milliliters. So to convert from liters to milliliters, we move our decimal point to the right 3 spots. 1, 2, 3. This is 75 milliliters. So what I as a scientist would do is I would go in, I would take 75 milliliters of my 2 molar solution, put that in my beaker, my Erlenmeyer flask, whatever, and then I would add enough distilled water to bring my total amount of my solution up to 0.5 liters, which is the equivalent of 500 milliliters, right? So I would add probably close to 425 milliliters of water to the 75 milliliters that I had taken. Okay, last calculation for the night is going to deal with molality. Remember, our formula for molality, which is our lowercase m, is moles of solute divided by kilograms of solvent. So this one's a little bit different in that way. Let's look at it. In the lab, a student adds 4.5 grams of sodium chloride to 100 grams of water. Calculate the molality. Well, 4.5 grams of sodium chloride compared to 100 grams of water. Remember, water is always the universal solvent. So we know sodium chloride is the solute. We've got to find out how many moles that is. So we have 4.5 grams of sodium chloride. 1 mole. This is going to equal, sodium is 23, I believe. And then chlorine is 35.45, I believe. So the molar mass is 58.45 grams. 5 divided by 58 is 0.077 moles. Now, to put that into our formula, that's going to be our numerator. And now we need kilograms of solvent. You take your grams, move it to the left 3 times, and you've got 0.1 kilograms. This is going to equal 0.77 molal solution. All right, that's it for today. Have a great day. I will see you on Wednesday.